Yeah, so good evening everyone. So I am Keshav. I am currently research scholar at IIT Kanpur. So this is week 7 of NPTEL course ME 111, okay, which is applied numerical methods. So this is a problem solving session for week 7. So till now what we have done in week 1 we have covered root finding methods. There we have discussed about bisection method, then Newton-Raphson method. These these were used to find out the roots of the equation having one unknown. Okay. Then in week 2, basics of programming has been discussed. By basics of programming means basic array operation and mathematical operations using Python. Then in week 3, solution of system of linear equations and non-linear equations has been discussed. There two type of method has been discussed. First one was direct solver. There we have seen, I think, LU decomposition method and Gauss elimination method. And second one was what? Iterative method or iterative solver. Their Jacobi iteration and Gauss seidel iteration has been discussed. So of means what? This is kind of problem AX equal to B type of problem. This is part of linear algebra. AX equal to B type of problem. And we have also seen that system of non-linear equation can be converted into system of linear equations using this Taylor series expansion and applying this Newton-Raphson method. Then that system of non-linear equations that has been converted to a system of linear equations, series of system of linear equations that can be solved using the linear solver like direct and iterative solver, which means Gauss elimination, LU decomposition, or Jacobi or Gauss seidel iteration. Then after we have seen the eigenvalue problem. Eigenvalue problem means what? AX equal to lambda X type of problems we have seen. There we have seen a method known as power method to find out the highest eigenvalue and its corresponding eigenvector. Means was the lambda max modulus and corresponding x we have found. Then power method. Then by using inverse power method, we can find lambda minimum, absolute value of lambda minimum. Whichever will be the minimum lambda, its value will be find. For that, their absolute will be minimum and their eigenvalue. Then what we have seen? We have seen then by shifting in inverse power method, we can find out the other eigenvalues and corresponding eigenvectors. Okay. In week 5, then we have completed till week 4, we have completed the linear algebra part. Then we have moved towards the calculus part. So there was one problem that we have seen in whatever the calculus we have studied that can be applied for a function that are continuous or piecewise continuous. But in numerical methods, we know the values only at a discrete point. So at these discrete point, how we can find out the differentiation of a function. And we have also seen knowing the discrete points, we can find out the function using the interpolating polynomial method, like Lagrange interpolating polynomial and other interpolating polynomials. Then we have seen in last week, week 6, we have seen what? Numerical integration. In numerical integration, what we have did? First, we have interpolating polynomial. First, interpolating polynomial we have found out. Then we have integrated it, right? So this is what? This is week 6. So here we will going to discuss how we can solve ordinary differential equation using numerical method. Okay. So before going to the numerical solvers for the ordinary differential equation, let us revise some of the basics of ordinary differential equations. So in general, ordinary differential equation can be written as a sum function phi, which is a function of x, y. Here x is what? X is a known independent variable and y is unknown dependent variable. Okay. So any function, any ordinary differential equation can be represented as in general form some function phi, where phi is a function of x, y, dy by dx, d2y by dx, similarly till nth derivative of it equal to 0. This is what? This is nth order ordinary differential equation. Okay. So y is dependent variable, which is unknown. If there are more than one unknown, then partial differential equation or partial derivative comes into picture. Okay. So ordinary differential equation can be of many types. One categorization we can make that linear ordinary differential equation and non-linear ordinary differential equation. So when it is called linear, then y and its derivative is multiplied with constant and functions of x only. Then it is called as what? Linear. Means what? You will see only y multiplied by some function of x or y multiplied by some constant. This y or derivative of y's. Okay, like that. Then it is called as linear. Means what? The degree, the what we call order, degree of the y will be, the power of y will be always 1. Okay. Now why differential equations are very important? Because any natural phenomena where unknown variable changes with respect to other known variable, where the change is important, and wherever the change is important, there partial differential equations comes into picture. That's why differential equation comes into picture. So differential equations are very important to define the natural phenomena that are occurring. Okay. So in your high school or, oh my god, my internet. Hello, am I audible? The power got shut down here. Okay, so maybe I need to join via my only via my iPhone, iPad, sorry. Otherwise it will get discharged soon, my laptop. So let me continue that. We will hope that in some time the power will come back. Okay. So the first kind of method can be separation of variable, where you have some dy by dx equal to some function f x y, and you can, by some manipulation, you can change this into some function v of y multiplied by dy equal to u of x multiplied by dx. Okay, this can be done. So this is called separation of variable method. Then exact type of ODEs is also a type of ordinary differential equations, when we have m dx plus n dy equal to y, zero type of a differential equation. where m and r are the function of both x and y. Okay, when this is called exact, when this whole m dx plus n dy can be written as du. Okay, when this will be possible, when del m upon del y will be equal to del n upon del x. Means what? The function that is multiplied by the dx, if we take the partial derivative of that with respect to y, and function that is multiplied by dy, if we take the partial derivative of that with respect to x, and if both are equal, then it can be called as exact ordinary differential equation. Then there can be a homogeneous ordinary differential equation that can be solved by substituting z equal to y by x. Suppose you have dy by dx will be equal to x square plus y square plus divided by 2xy. So you can see here x and y multiplied here, and here x square y square. So everywhere you can see variables power is 1. So this can be called as homogeneous. Okay. Now these are the easy thing that we have discussed, that we have studied earlier. Okay, then linear ordinary differential equation can be solved using the integrating factor method. And there also there has been a method for Bernoulli equation. Means was suppose we have a linear equation, and here we have some y. Okay, then you divide this y, function of y, in the left hand side, and whatever you get here, a by, suppose here we are getting a by y, so you want here only y, so you just assume whatever you are getting here, you assume some variable z equal to whatever the multiple of this a, you assume directly here it is y, so 1 upon y, then you differentiate it and find out the value. Okay, now we come to the main part of our discussion for week 7, that is the numerical method to solve the ordinary differential equation. Okay, so ordinary differential equation can be of two types. One is the initial value problem, another one is a boundary value problem. Initial value problem can be solved using Euler method or Rungge Kutta method. Okay, what initial value problem we will discuss in some time. And boundary value problems can either be solved by converting it to initial value problem. That method is known as a suiting method, or it can directly solve by converting it into a system of linear equation. Means what? Ax equal to b type of system using finite difference method, which is also called as FDM, or finite volume method, which is called as FVM, or finite element method, which is called as FEM. Okay, now we'll see initial value problem. Okay, so suppose we have an ordinary differential equation phi equal to phi, which is some function of x, y, y prime, y double prime, dot dot, y to the n prime. Okay, this we have. So what will be the simplest form? If its order is 1, so n equal to 1, if we put n equal to 1, then we can say dy by dx equal to f, where f is a function of x and y. Okay, and since it is a first order derivative, so we need only one initial condition. Still my voice is breaking. Hello. Hello. I think now my voice is clear. Yeah, so power came back, so there is no issue now. So now the simpler form we can write dy by dx equal to some function f, where f is a function of x and y. Okay. Since it is a first order derivative, so we need only one initial condition. So here initial condition is y at x equal to x naught is y naught. Okay. This is what? This is a first order initial value problem. Okay. Now this can be solved by Euler method. How we can solve using Euler method? We will use finite difference method to create a difference equation. How we can create the first, whatever the domain is, we will discussize the domain. So suppose we have domain from x equal to x naught to some x equal to x l. Okay. So we will discretize this into small steps. H, this is known as a step size or grid size. That will be equal to xi plus 1 minus xi. If this discretization is uniform, which means what? All this step size will be same. Okay. And if any of this step size is different, then that is called a non-uniform grid. Okay. So this dy by dx by using what? By using finite difference method, this y prime can be written as yi plus 1 minus yi divided by h plus some order of h will be equal to f at xi and yi. Fine. This is what? This is we have studied in the, I think, last to last week in numerical differentiation part. Now, if you take this h out other side, so we can get like that yi plus 1 will be equal to yi plus h, which is a step size, multiplied by the function f at xi yi. Okay. Now, this is what? This is locally what? This is locally order of h square. Okay. But when you take the whole, when you see the global picture, there will be a summation term. So this order of h square will come as n multiplied by order of h square. That n can be written as the whole domain divided by the small h. So one h will be cancelled. So globally it is what? Order of h. Okay. So this is the formula. This is the formula for Euler method. Yi plus 1 will be equal to yi plus h multiplied by function xi comma yi. Function at xi and yi. Okay. This is called as explicit Euler method. Why explicit? Because you see here yi plus 1 is unknown. So yi plus 1 is coming in the left hand side, and all other things that are in right hand side, yi, xi, yi, h, all are known. So yi we are directly calculating. Okay, not solving. That's why it is called explicit method. But there is one issue in this method, in this explicit Euler method, that here as we move forward, suppose for one interval you have calculated, then for suppose you have calculated using y0, you have found out y1. Okay. Then using y1, you have found out y2. Using y2, you have found out y3. Okay. So as you move forward, the error, some error will be involved here, some error will be involved here, some error will be involved here, the truncation error. So these errors will be accumulate as we move in the iterations. Okay. So this is the issue with explicit Euler method. This can be avoided by using very small grid size or by using the implicit Euler method. What do we mean by implicit Euler method? Here the function f we do not write at xi and yi. We write this function at xi plus 1 and yi plus 1. So if you use this function and manipulate it, so you will get what? Y plus 1 minus h multiplied by f of f at xi plus 1 and yi plus 1, that will be equal to yi. So here this is unknown, so this function is also unknown since y is unknown here. So this is kind of a linear equation. No? So this will lead to a system of linear equation, okay, that needed to be solved. So here we have seen what Euler method is was locally order of h square, and it is globally order of h. Okay. So how can we improve its accuracy? To improving the accuracy, the Kutta method has been introduced. Okay. Basically, what we are doing, we are having some dy by dx equal to f of x comma y. So this can be written as y prime equal to f of xy. We are doing nothing. We are integrating both sides. So this will lead to y prime dx integration, that will lead to y. And this right hand side, what we are doing, we are integrating it numerically. Okay. So numerical integration already we have studied in last week, trapezoidal method and Simpson 1/3 rule for numerical integration and Simpson 3/8 rule for numerical integration. So that are kind of accurate compared to that one. So suppose I am using trapezoidal method to find out the numerical integration. If I use that, what is the formula that I will get? I will get yi plus 1 minus yi, that will be equal to h by 2 function f at xi plus function f at xi plus 1 plus yi plus 1. And its accuracy will be what? Order of h cube. Okay. So it is what? It is locally what? Order of h cube, and it is globally order of h square. Okay. So, but here you see, this is what? This is my unknown. Since x, y, I plus 1 is not known, which means what? This whole term is unknown. Okay. So how we can find out this unknown term? This can be predicted using the Euler method. Okay. So what we do, first we find some yi plus 1 star, that will be equal to yi plus h multiplied by k1, and that k1 will be what? That k1 will be f at xi and yi. Okay, the function value at xi and yi. Okay, then yi plus 1 will be equal to yi plus h by 2 k1 plus k2, and this k2 is what? This k2 is what? Function f at xi plus 1 yi plus 1. Okay, which means what? Function at xi plus h plus yi plus h. H is what? Step size. So this is known as second order Rungge-Kutta method or Hume's method. Okay. So here what we have found? We have found yi plus 1 will be equal to yi plus h by 2 k1 plus k2. Okay. And this k1 is equal to function of I comma yi. Okay. And k2 is what? K2 is what? F x I plus 1 y I plus 1. Okay. So this is what? This is locally h cube order of and globally h square. So by seeing that, we also can say that this Euler method is nothing but a first order Runge-Kutta method. Okay. So in general form, we can write as yi plus 1 will be equal to yi h multiplied by summation of j equal to 1 to n aj kj, and its order will be locally order of h to the power n plus 1. This n can be defined by the user. So k1 will be what? K1 will be function at xi yi, k2 will be what? Function xi plus some p1 multiplied by h, and yi plus some factor of k1 that will be included, and h. Okay. Similarly, k3, k4, and kj can be defined in general sense. This is called as nth order Runge-Kutta method. But the most commonly used Runge-Kutta method is fourth order Runge-Kutta method. Okay. Fourth order Runge-Kutta method means what? It will be globally fourth order accurate, and it will be locally fifth order accurate. Okay. So if you use this kind of formula, this formula you use this generalized form for the kth for fourth order, and this these terms wherever the y is involved, we write using the Taylor series, then we will get what? We will get this expression for iteration yi plus 1, that will be equal to yi h by 6 k1 plus 2k2 plus 2k3 plus k4. Okay, this is what we will get, where k1 is what? Function at xi yi, k2 is what? Function at xi plus h by 2, comma yi plus h by 2 multiplied by k1. Okay, similarly k3 will be what? Function at xi plus h by 2 plus yi plus h by 2 multiplied by k2. Okay, so we are incorporating or including the previous k that has been calculated. Okay, then k4 is function at xi plus h yi plus h multiplied by k3. Okay, fine, clear. So now we will solve some problem using this method that had been discussed. So this is the first problem. You please try to solve, and meanwhile I will also solve this. Okay, so the problem is, we need to solve this problem using Euler method. dy by dx equal to x square plus y square. Here initial condition is giving y at x equal to 0 is 0. Okay, we need to take the step size is 0.5, and we need to find y at x equal to 0.5, y at x equal to y at x equal to 1, y at x equal to 1.5, y at x equal to 2 and 2.5. Okay, we need to round off our answer up to 3 decimal places. Okay, so I hope you would have written this question. Okay, so this is the question. Please try to solve. So here, what is the function here? So this is a kind of equation y equal to fx comma y. Okay, so here what is what? Here f of x comma y is what? X square plus y square. Okay, and h is what? H is 0.5. Then we can write, suppose this is my grid. Okay, this is my grid 0, 0.5, x equal to, this is the x values, 1, 1.5, 2, 2.5. Okay, so this is what? This is I equal to 1, I equal to 2, I equal to 3, I equal to 4, I equal to 5, and I equal to 6. Okay, so we need to find, suppose I want to find y. We know the expression for Euler method, yi plus 1 will be equal to yi plus h multiplied by f of xi yi. Okay, so if I want to find here y2, so that will be equal to y1 plus h multiplied by x1 multiplied by f at x1 comma y1. Okay, now you replace the value of this f. Here f is what? X1 square, y1 square. Now you put the value. So from here, y at x equal to 0.5, this will be what? Y1 is 0, plus from initial condition, this is 0 at x equal to 0, plus h value of h 0.5, x square 0 square, plus y is 1, y1 is what? 0, 0 square. That will lead to value 0. Okay, so this will be what? My 0. Clear? Now suppose I am writing for y3, that will be equal to y2 plus h multiplied by x2 square plus y2 square. So this is what? This is y at x equal to 1. Okay. So y3 will be what from here? 0. H is what? 0.5. This is what? 0.5 square plus 0 square. So from here, what value will we get there? It will be 0.125. Okay. So this is what? 1, 2. Oh, sorry. 0.125. Here. Now we want to find y4. Y4 that will be equal to y at x equal to 1. That will be equal to y3 plus h x3 square plus y3 square. Now you put the value. Y3 is what? 0.125 plus h is 0.5. X3 is what? 1 square plus 0.125 square. Okay. If you calculate that, y4 will come, which is nothing but y at x equal to 1. That will be equal to what? Okay. 0.633. Okay. Good. Now if I want to find y5, that is equal to y at x equal to 1.5, right? Have I made some mistake? 1, 2, 3. Oh, sorry. This is at 1.5, na? Now we want to find at 2. So this will be equal to what? Y4 plus h multiplied by x4 square plus y4 square. So this is what? 0.633 you put. Here h is what? 0.5 you put. Here x4 is what? X4 is what? 1.5 square. This will be what? 0.633 square. Then you calculate the value. Similarly, y6 will be what? Y at x equal to 2.5. That will be equal to y4, sorry, y5 plus h x5 square plus y5 square. So this value is 0.5. This value is what? 2 square. This value is what? Okay. So it comes around 958. So this is 1.958. Okay. So this is 1.9958 square. So how much value it will come? So if I calculate 1.958 plus 0.5 multiplied by 2 square plus 1.958 square, this will be 5.875. Okay, fine, clear. So whatever the value we have found, I just want to write down here. Okay. So first value was what? 0. Second was 0.125. Third one was what? 0.633. 1.958. Then other value was what? Last one? 5.875. Okay. So this is the answer. Now we move toward the next problem. So this is the next problem. Okay. So here what we need to do, we will use the step size as 2. Okay. And we'll use the fourth order Runge-Kutta method to solve this differential equation dy by dx equal to x plus y. Their initial condition is y at x equal to 0 is 0. We need to approximate our answer, round off our answer to third decimal place. Okay. Then we need to find k1, k2, k3, k4. Then by using these, we need to find out y at x equal to 2. Okay. Please try to solve this problem. Dy by dx equal to x plus y. Step size is 2. And initial condition is y at x equal to 0 is 0. Okay. So here what we have y prime. Maybe I use this. Here we have y prime equal to f of x comma y, that is x plus y. Okay. This is what we have. And h is equal to 2 for this case. Okay. So from Runge-Kutta method, this will k1 will be equal to function at xi yi. Okay. K2 will be what? Function at xi plus h by 2 comma yi plus h by 2 multiplied by k1. Similarly, k3 will be equal to function value xi plus h by 2 yi plus h by 2 multiplied by k2. Then k4 will be what? Function value at xi plus h yi plus h multiplied by k3. Okay. Then by knowing this value, we can find out xi plus 1, that will be equal to yi plus h by 6 k1 plus 2 k2 plus 2 k3 plus k4. Okay. Here xi is 0, yi is 0. Okay. So xi plus 1 will be what? Xi plus h, that will be equal to 0 plus 2. So xi plus 1 will be equal to 2. So if we find yi plus 1, that will be equal to y at x equal to 2. Okay. So we need to put these values and find out the values now. Okay. So from here, k1 will be what? Xi plus yi. Okay. This will be what? Xi is 0 and yi is also 0. So this will be 0. Okay. Now here, this will be xi plus h by 2 plus yi plus hk1 divided by 2. So this value is 0. This value is 0. K1 is 0. So this will be equal to h by 2. That will be 2 by 2, which means 1. So K2 is what? 1. Now K3. So xi plus h by 2 plus yi plus h multiplied by K2 by 2. Okay. So this is 0. This is 0. So 2 by 2 plus 2 by 2 multiplied by 1. This will lead to what? 1, 1 plus 1, 2. This will be equal to 2. Now this value, this will be xi plus h plus yi plus h multiplied by k3. 3. So this is 0. This is 0. So 2 plus 2 multiplied by 2, that will be equal to 6. So k4 is 6. So now we need to find this yi plus 1. So yi plus 1 will be equal to y at x equal to 2. So if I put, this is what? 0. So 0 plus h is what? 2 by 6. K1 0 plus 2 multiplied k2 1 plus 2 multiplied by k3 is what? 2 plus K4 is what 6. So 6 plus 4, which what 10, 10 plus 2, 12, 12 divided by 6, 12 multiplied by 2, 12 multiplied by 2 will be 24, 24 divided by 6, that will be 4. Okay. So 0 answer will be what? Here it will be 0. This will be 1. This will be 2. This will be 6. This will be 4. Clear? You see here also I have solved it. Yeah. Right? Okay. So now we'll move ahead in our discussion. So where were we? We were discussing about the Runge-Kutta method. No? So this is the fourth order Runge-Kutta method formula. Okay. Now we have discussed the y prime equal to f of x comma y, means what? First order. No, this is first order ODE initial value problem. So this we have discussed how to solve, and we have also seen. Now, if we want to solve higher order initial value problem, how we can solve it? So this higher order, nth order ordinary differential equation or nth order initial value problem can be converted into a n first order initial value problems. How we can convert? Now we will see. Suppose we have an example. We want to solve in domain x equal to 0 to 1. In this domain, we want to solve this differential equation y double prime minus 2y prime plus 2y equal to e to the power 2x multiplied by sin x. We have initial condition y at x equal to 0 is minus 0.4 and y prime at x equal to 0 is minus 0.6. This we have. Okay. So what we do, we will assume y equal to u1 and y prime equal to u2. Okay. So just you put here in this equation, you put, so this will be what? This will be u2 prime. This will be what? Plus 2u1. Sorry. Oh, sorry. So this will be what? U2 prime. This will be what? U1 prime. And this will be what? U1. You put these values, then this equation can be converted into this form. U2 prime will be equal to some function f2. F2 will function of x, u1 and u2. And this can be written as 2u2 minus 2u2 minus 2u1 plus e to the power 2x multiplied by sin x. Here what we have did, we have replaced y double prime as u2 prime and y prime as u2 and y as u1. Okay, this is what we have did. And second equation from here we will get that y prime u2 from here. If you put directly, so this will be what? U1 prime will be equal to u2. Okay, so here initial condition is what? U1 at x equal to 0 is minus 0.5. So this is what this is my one equation. Okay, and this is my second equation. So what we have got? We have got two ordinary differential equation in first order. Okay. Now this can be solved using the Runge-Kutta method. How? Fourth order, if I'm using fourth order Runge-Kutta method, I can write k1 is equal to what? Function at xi and yi. This can be written as k1 for both equation, for first equation and for second equation. So kj1 that can be written as function at xi, u1 at I and u2 at I. So if I am writing for the first equation, I can write function as f1. So for the first equation f1, xi comma u1 at I, u2 at I. Similarly, if I want to write k1 for second equation, sorry, for second equation, I am writing one value. So for here, that will be f1, sorry, f2, second equation, xi, comma u1 at I and u2 at I. Similarly, k2 for jth equation, k3 for jth equation, and k4 at jth equation can be written. Okay. So if I am writing k2, that will equal to xi plus h by 2. This is simple. Now here y1 at ith plus h by 2. Now there will be a multiple. So multiple will come from the first equation. Since here is u1, so u1 multiple will come here. Earlier one k1 from the first equation. Similarly, in this case, u2 at ith point, then plus h by 2, then the multiple will come from the first equation, and k1 from the second equation, sorry, k1 at from the second equation. Similarly, if I am writing k3, so u1 at ith plus h by 2 multiplied by from first equation k2 value. Similarly, u2 plus h by 2 k2 value from the second equation. Okay, like that k4 also we can write, that will be equal x I plus h function value xi plus h u1 I plus h, then k3 will come, but in u3 k3 will come from the first equation, and in u2 k3 will come from the second equation. Okay, now once we have found out this kj's values, kj1 kj2 kj1 kj2 similarly kj2, अरे यार हाँ हाँ मतलब kj's value for different equations, if we found, then we can find out the u1 and u2 I plus 1th value. So u1 I plus 1th value will be equal to u1 at I plus h by 3 k from first equation 1 value, k2 from first equation plus 2 multiplied by k3 from first equation plus k1 4. So this is first index is what? Equation number, and this is the k number, no? K number, whatever. Okay. So by using this equation, now we can find out the u1 and u2. Once we have found the u1 is what? u1 is equal to y. So we have find out the y value. That was the whole problem we want to solve for y. And since we have found out the y1, this will equal to y only. Okay. So nth order initial value problem can also be solved. That then this yi plus 1 will be equal to ui plus 1 will equal to ui plus k coefficient multiplied by a. So a will be what? h1 h by 6 h by 6 h by 6 transpose means a column vector. Similarly, this u will be u1 u2 u3 un column vector, and there will be a coefficient matrix of k. So k1 k2 k3 k4 dot kn from first equation, k1 k2 k3 k4 kn from the second equation, k1 k2 k3 kn from the nth equation. Okay, like that we can solve any higher order initial value problem using by converting into the n number of first order initial value problems. Clear? We'll see one problem. From there it will be clear. Okay, not now, that will be a practice problem, so we'll see at last. Okay, so this OD solver can be used for solving any ordinary differential equation, that is initial value problem. Okay, so one special kind of problem can be a growth model type problem, population growth type problem. Okay, so there can be population growth type. There are multiple type of models like exponential model, logistic model, or well-host model, or predator-prey type of model, that is known as Kutta Volterra model. Okay, so in exponential type of model, we assume that the population is increasing or decreasing with respect to time with some growth rate a. Okay. So if x is the population at time t and growth rate is a, then it can be written as dx upon dt will be equal to ax. If with some initial condition at t is equal to 0, the population is x naught. If you solve this differential equation, you will find x equal to x naught e to the power at. So suppose if a is positive, means what, our population is increasing. So if you plot this x at t is equal to 0, so this will come like that, some like that function. So it is going to infinity as time increases. Okay. So this is a kind of unbounded population. But population cannot be unbounded. There will be boundation for in the population. There will be a resource constraint and other criterias that will stabilize the population. Okay, so that's why this unbounded term that is unrealistic. Another method is came, that is logistic method. Logistic method tells that there will be some carrying capacity. Means what, there will be a maximum sustained population beyond which population will not increase. So if P is the carrying capacity or maximum sustained population, its differential equation can be written as dx upon dt will be equal to ax 1 minus x upon p with same initial condition. Now if you solve, you will find this as an analytical solution. Okay. So now if t tends to infinity, our population will converge to p, the carrying capacity. Okay. These both methods has limitations. What limitation? That it do not consider the other factors. Like suppose if we are considering the population of deer, so that will depends on the population of the tiger also, and vice versa. If we are considering the population of the tiger, that will depend on the population of deer. Means more tiger will, if there is more tiger, there will be less deers. And similarly, if there is less deer, there will be more tiger. So this method, petrel play method, is known as Volterra model. Okay. So this is the differential equation for that, a group of differential equations. So the population are given as xt and yt, which is the population of predator and prey at time t. A and C, A is what? Growth rate of the prey, and C is what? Death rate of the predator. In B and R, this B and this B are interaction parameter between prey and predator. Okay. So these two equations, if you eliminate T, then you can solve for X and Y. You can form a differential equation in X and Y that can be solved. But if you wish to solve for T, you need to go for this method that has been discussed. I don't think there is much to explain here, so I'm moving ahead. So till now what we have seen? We have seen initial value problem. There we have seen first order also, and any journal nth order also. Okay. Now we move toward the boundary value problem. When boundary value problem come, when there are some conditions at the boundaries. Okay, so this is one boundary. Suppose this is the second boundary. So we have two boundaries. So minimum, there will be minimum two boundaries. So these boundary values problems always second order or higher order ordinary differential equation. Okay. So how we can solve this problem? This boundary value problem can be solved by converting into a set of initial value problem. Okay. So we have already seen this, how to solve initial value problem. If we convert this boundary value problem into an initial value problem, then it can be solved easily. So this method to converting a boundary value problem into an initial value problem is known as, this method of solving is known as sorting method. Okay. Or we directly convert this boundary value problem into a set of linear equation ax equal to B type of problem. How we can convert? By using the finite difference method. Then this linear system of linear equation can be solved using the linear solver. By linear solver, I mean Gauss elimination method solver or LU decomposition or some iterative solver like Gauss-Seidel or Jacobi-Truson. Okay. So now we'll see the first method, that is converting the boundary value problem into a initial value problem, that is known as shooting method. So let us see one problem, that is Blasius problem. So this is the differential equation that comes when we solve laminar boundary layer over flat plate. So this is the governing equation of laminar boundary layer over a flat plate. F triple prime plus 1 by 2 F multiplies F double prime equal to 0. And we have F at x equal to 0 is 0. F prime at x equal to 0 is 0. And limit L tends to infinity, F prime at x equal to L is 1. So this is our problem. So this is initial condition, this is initial condition, this is some boundary condition. Okay. So I want to convert it into a initial value problem. So we need to assume some initial condition to convert into a two initial value problem. How we can convert it? So I am assuming F double prime at x equal to 0 equal to A and F double prime at x equal to 0 equal to B. Okay. And the same equation and other same initial condition we have. So these two are this is first initial value problem. This is second initial value problem. Okay. And this A and B, I need to choose such that when I solve this and come up to the solution, when I solve this and find the solution, by that solution, if I find F prime at x equal to L, that gives me alpha. And similarly, F prime at x equal to L, that gives me beta from the second equation. Here multiple alpha minus 1, beta minus 1 should be less than 1. Okay. This should be satisfied with, then only our this guess is correct, otherwise not. If this is not coming, we'll change our initial guess. Okay. Now, right now, I am assuming that this condition is satisfied. Okay. So what we will do? Now we will set f double prime equal to a plus b by 2. Okay. Means what? Some bisection type of algorithm we will apply. Some a, we have made some a guess, we have made some b guess. Now we will take its average a plus b by 2 and we will evaluate from here, solve and evaluate f prime at x equal to L. That will lead to some gamma. Okay. Now here we have some 1, here we have some alpha, here we have some beta. If this gamma comes left side of 1, and it will obviously come right side of a right side of alpha. So if this come left side of a, I will replace alpha by gamma. And if it comes right side of 1, I will replace beta with respect to with gamma. Okay. Just like we have did in bisection method. Then again, my new a plus b by 2 will be what? Whatever will come, then a plus b by 4 I will take, like that. In is slowly I will move till my solution converges. Okay. So this is my converging criteria. Clear? So this is the shooting method. So we will make some initial guess, two initial guess. A and B such that when we find out our boundary condition, their multiple should be negative, means alpha minus the value whatever which was given in the question, alpha minus 1 multiplied beta minus 1, that should come less than 0. If this is satisfied, then my next iteration value will be what? F double prime at 0 will be equal to a plus b by 2. Okay, there we will find gamma. That gamma will replace using the bisection method kind of algorithm. Similarly, we move ahead and the sorting value problem. Then we comes towards the finite difference method. Means what? The boundary value problem will be solved directly and it will be converted into the set of linear equation, and this linear equation will be then solved. Okay. So let us consider a physical problem to understand that. So I have a fin here. So this is called fin. So this is the extended surface of fin. So surrounding temperature is T infinity. Temperature at the base is T naught, means at x equal to 0 temperature is T naught. I am assuming at x equal to L temperature is T0. And if I find out the governing equation for this, it will come like that: d2 by dx square plus a upon 1 upon a dA upon dx multiplied by dt upon dx minus hp upon ka t minus t infinity. The derivation is not important. Now we will try to non-dimensionalize it. Non-dimensionalization means what? We'll convert the temperature into non-dimensional temperature and this length into a non-dimensional length. If you do that, we'll find the differential equation d2 theta upon dx square plus 1 upon a d upon dz multiplied by d theta upon dz minus hp upon hpl square upon ka multiplied by theta will be equal to 0. What is the boundary condition now? If you put here at z equal to 0, t is what? Here we will do t naught. So this will be cancelled here and here it will be cancelled. So it will come as 1. So at z equal to 0, theta is 1. At z equal to 1, theta is equal to 0. Now we are simplifying the problem by saying the area and perimeter are constant, and I am assuming this hpl square upon ka is equal to m square. So this will lead to a d2 theta upon dz square minus m square theta will be equal to 0. Now this equation can be solved analytically. So solution will be what? Theta will be equal to some constant b multiplied by e to the power mz plus c e to the power minus mz. Okay. Then you put the boundary condition and find out the solution. The solution will come as theta will be equal to sine hyperbolic m minus mz divided by sine hyperbolic of m. Sine hyperbolic is what? Sine hyperbolic of x, if I am writing, this will be equal to e to the power x minus e to the power minus x divided by 2. Okay. You replace that, then you will find this solution. Okay. So this is what? This is the analytical solution. How I can find out the numerical solution? So to find out the numerical solution, first thing what we need to do, first step is what? We will discretize the domain. So we have some continuous domain from z equal to 0 to z equal to 1. Okay. So we will discretize the domain. So some discretization I will do. This discretization may be uniform or may be non-uniform. If each step size is equal, if each of these step size are equal, then it is called uniform discretization. If any of them is different, then it is called non-uniform discretization. Once I will discretize the domain, I will find out the discretized differential equation. How? By using the either of finite difference method, finite volume method, or finite element method. Here we will use finite difference method to discretize the governing equation. Once we will discretize the governing equation, we will find out the boundary condition in discretized form. Okay. Then once we have found all three steps, we will solve the system of linear equation that we will get after step 1, 2, 3 by using the linear solvers. Okay. So here, suppose we are assuming uniform grid. By uniform grid means what? for any I from 1 to n minus 1, if I find zi plus 1 minus zi, that will lead to some delta z always. Okay. So these points are called grid points. These points are called grid points, and this is called grid size, step size or grid size. So how we can do that? Here we have d2 theta upon dz square minus m square theta. Okay. So d2 theta upon dz square, we can write using the finite difference method as theta I minus 1 minus 2 theta I plus theta I plus 1 divided by delta z square minus m square theta. I am writing theta as I, theta I. Okay. Now, if you do some manipulation, you will get theta I minus 1 plus b multiplied by theta I plus theta I plus 1 will be equal to 0. B is what? If you find out, B will be equal to minus 2 minus m square delta z square. Okay. So this is what we will get. This is for I equal to 2 to n minus 1. At I equal to 1, there will be a boundary condition, and at I equal to n, there will be a boundary condition. So let us go to the boundary condition now. So now we need to find out the discretized boundary condition. So theta I at I equal to 1 is what? 1 from theta equal to 1 at z equal to 0. So this is what I equal to 1. So at I equal to 1, theta is 1. Similarly, at I is equal to n, theta I is what? 0. Now, if I write in, if I just write it for I equal to 2, 3, dot, dot, n minus 1. So for I equal to 1, what we have? Theta equal to 1. For I equal to 2, we have theta I minus 1 plus b theta I plus theta I plus 1 equal to 0. Similarly, for I plus 2, we have theta I minus 1 plus b theta I plus theta I plus 1 equal to 0. Similarly, for n minus 1, I equal to n minus 1, we have theta I minus 1 plus b theta I plus theta I plus 1 equal to 0. Similarly, at I equal to n, we have theta I equal to 0. So we have what? Here we have considered n grid point that lead to n equations and n unknowns. Okay. So n equation, n unknown, and we have n equations and n unknown that can be solved using, this is the linear equation that can be solved using linear solver. So now I am writing it into the n equation n unknown into a format of matrix. I am writing it into a matrix format. So for first equation, coefficient is 1, theta 1 equal to 1. Now in second equation, from here it will come 1, from here it will come b, from here it will come 1. Similarly for next equation, from here it will come 1, from here it will come b, from here it will come 1. Similarly for the last equation, we will have theta equal to 0. So multiple of theta is 1. So here it is 1, theta n, and right in RHS it is 0. For the first equation it is 1, and for other equations RHS is what? 0. Okay. So here if you see that we have a n cross n coefficient matrix. So total number of element will be what? N square. But number of non-zero element is what? Most of the elements are 0. 3 from here, 3. It can come up to 3n, from n to 3n. So number of non-zero element will be from n to 3n. If it is less than n, then we will not able to solve this problem. But if it less than, but it will come always less than 3n. Okay. So there is one diagonal term, na? B is the diagonal term. And we have some terms just above the diagonal and below the diagram. So only three of such these things are we have non-zero, and other are what? 0. So this is called as tri-diagonal matrix. Okay, this is called as tri-diagonal matrix. So tri-diagonal matrix, diagonal will be non-zero, and above that is non-zero, below that non-zero, other will be 0. So this is called as tri-diagonal matrix. Okay. This is called as tridiagonal matrix. So as you have seen earlier, here most of the terms are zero. Most of the terms are zero. So the coefficient matrix is a sparse matrix. If most of the terms are zero, then matrix is known as sparse matrix. Okay. So there will be very few non-zero terms. So how we can solve this tridiagonal matrix or tridiagonal type of system? This can be solved by using this can be solved using the Gauss elimination method. But if we use the Gauss elimination method, some of the or most of the zero term will be converted into a non-zero term. This is the problem. So we want to utilize this benefit that most of the terms are zero. The matrix is sparse. So for that solution of tridiagonal system, one algorithm is generally used that is known as the Thomas algorithm. Okay. So suppose we have a general tridiagonal system ai xi minus 1 plus bi xi plus ci xi plus 1 equal to di. I goes from 1 to n. Okay. So this matrix is what? Sparse matrix. So we will never store the entire matrix. Rather than what we will do, we will store it into a one-dimensional arrays. Okay. So three one-dimensional arrays will be used to to store the entire matrix. Okay. So if I write this tridiagonal system into a matrix form, it will be equal to b1 c1 plus other sum will be 0. Then in second row that will be a2 b2 c2. Third row a3 b3 c3. an minus 1 bn minus 1 cn minus 1. Here an bn. And column vector will be what? This is the unknown x1, x2, x3, xn minus 1, xn. In right hand side, d1, d2, d3. So this we wish to solve. So we will use the methods same as Gauss elimination method. Okay. What we do in Gauss elimination? First we do forward elimination. Then what we do? We do back substitution. So when we are doing the forward elimination, what we try to do, we try to make these terms, the term below the pivot, the diagonal element is my pivot. So term below the pivot, we try to make it 0. Suppose if my B2 is pivot, I try to make all the terms that are below B2 0. This is what we try to do in forward elimination. Here the term that is below B2 is only A3. Similarly, the term below B1 is only A2. So we try to make this A2 and A3 0. Okay. How we can make that? This forward substitution for all rows, we try to make this ai equal to 0. How we can do? So we write some equation 2 new that will be equal to equation 1, equation 2 old minus equation 1 multiplied by the element that is below the equation 1 divided by the pivot element. Okay. So if we do that, our A2 will come as 0 and our C2 will no change. And B2 will be equal to what? B2 will come as new B2 will be equal to B2 minus C1 multiplied by A2 divided by B1. B1 is pivot element. Similarly, D2 will be what? D2 will be equal to D2 minus D1 A2 upon B1. Similarly, for row 3, if I write equation 3 new will be equal to equation 3 old minus equation 2. If I'm taking equation 2, so B2 will be my pivot and A3 will be my element that is below the B3. So from by doing this, my A3 will come as 0, C3 will no change, B3 will be equal to B3 minus P2 A3 B2 divided by B2. Similarly, D3 will be what? D3 minus D2 multiplied by A3 divided by B2. So in the generalized format, I can write for I equal to 2 to n, what I am doing, I am defining some R, that R will be equal to AI divided by BI minus 1. Then I am writing BI will be equal to bi, I am replacing bi as bi minus ci minus 1 multiplied by r. Similarly, di will be equal to replace to di minus 1 multiplied by r. And we do not write anything for a and c. Simply a will be what? 0 and c will be no change. Okay. Now, after that, what we will do? We will do the back substitution. So back substitution for the nth equation, we will get here what we have some a n, b n we have, and here we have some d n. Now after the forward substitution, this becomes d0. So theta n, suppose here theta n minus 1, like that some term was there. So this is 0. So from here we will get x n. Oh, sorry, this is x, not theta. From here we will get xn will equal dn upon bn. For n minus 1th equation, we will get x n minus 1. That will equal to b n minus c n minus 1 multiplied by xn. This xn is already known. Okay. Divided by b n minus 1. Similarly, in generalized format, I can write xn will be equal to xi will be equal to di minus ci xi plus 1 divided by bi, where my I goes from n minus 1, n minus 2, n minus 3 to n. Okay. So this bi is coming into the denominator, which means what? This should not be equal to 0. Okay. Otherwise, this solution will not be feasible. Clear? This is what has been discussed in week 7. Now we will try to solve a practice problem. Okay. So this is my practice problem. So just give me 1 minute. So this is my practice problem. Okay. So we need to write. So we want to write a computer program to solve ordinary differential equation using fourth order Rungge Kutta method. And this is the ordinary differential equation, which is what? Second order ordinary differential equation. Second order initial value problem. Na? Y at x equal to 0 is 0 and y prime at x equal to 0 is 1. Okay. We want to use the step size as 0.01 and we wish to solve this problem in 0 to 10 domain. Okay. So how to solve this problem? If you remember, nth order initial value problem can be converted into an first order initial value problem. Okay. Then this can be solved. So how? So here we have y double prime. What is the equation? We have y double prime plus y prime plus y equal to sin x. Okay. And what are the initial conditions? Initial condition, what we have? Initial condition we have y at x equal to 0 is 0 and y prime at x equal to 0 is 1. Okay. This is what we have. Now here what we'll do? We'll assume y equal to u1 and y prime equal to u2. Okay. So if you put here this value in this equation, from here we will get u1 prime will be equal to u2. Okay. And what will be the initial condition for this equation? Initial condition will be equal to u at x equal to 0 will be equal to 0. Okay. Second equation, what we will get? Simply you put here. So this y prime equal to u2 you put here. So u2 prime plus u1, sorry, u2 prime plus u2 plus u1 will be equal to sin x. Okay. So this can be written as, this can be rewritten as minus u2 minus u1 plus sin x. Okay. And what will be the initial condition here? Initial condition will be what? u2 at x equal to 0 is 1. Okay. So we have here, we have two equations now. Two initial value problems we have. So this can be solved using fourth order Rungge-Kutta method. So from here so this is my first equation. So this is my f1 x u1 u2. This is my what? This is my f2 x u1 u2. Okay. So from here, if I write f1 x u1 u2, that will be equal to what? Directly u2. f2 will be what? f2 will be what? X u1 u2 will be equal to minus u2 minus u1 plus sin x. Okay. This is what we have. Now from here, first j1. J is what? Equation number, and 1 is the k number. Okay. So j1 will be what? F of j x I comma y I. Okay. So from here, if I write k11, k11 will be equal to u2 at I. Okay. u2 at I. Similarly, if I write k21, that will be equal to, what? Minus u2i minus u1i plus sin xi. Okay. Similarly, I can write kj2, that will be equal to fj xi plus h by 2. Here, what is the h value? Here in the question, maybe I use some other. Here my h is what? 0.01. Okay. So, comma, u u1i u2i. Okay. So k2j will be equal to u1i plus h by 2. Now k1 is only, and here I am writing u1. So k from first equation and first value. Okay. Similarly, u2i plus h by 2, k from second equation first value divided by 2. Okay. So this is will be what? K2j. Now by using this, if I write k12, this will be equal to u2 i plus h, यार h2 नहीं, h ना, h multiplied by k 21 is already known, divided by 2. Similarly, if I want to write k22, that will be equal to what? minus u2 I so from here we can write this now. From here we can write this. Since we have, I think you got it now what I'm trying to say. So K22 will be what? F2 x I plus h by 2 comma u1 I plus k from first equation first value no, from second equation first value multiplied by h divided by 2 comma u 2I plus h by 2 k k from second k from what? Here it will be what? The first value we'll use from equation 1. First value from equation 1. First value from equation 1. From equation 2, first value. Okay. Similarly, if I want to write K3, okay, K third equation, अरे यार, K first equation, third value. This will be equal to F1 xi plus h by 2 comma ui 1 plus k will come from first equation, second value h by 2 comma u2I plus h by 2 k will come from second equation, second value. Okay. Now k second equation, third value f2 xi plus h by 2 comma ui 1, sorry u1I लिखना चाहिए ना मुझे. I should write u1I 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 plus k will come from second equation, second value k will come from first equation, second value divided by 2 comma u2I plus h by 2 from second equation, second value. Okay, so this value we will say only first function will be replaced by second function when we are writing for the second equation. Okay. Similarly, if I want to write for k, suppose first equation fourth value, this will equal to f1 xi plus h u1I plus h multiplied by k. K will come from first equation, third value comma u2 at I plus h multiplied by k will come from the second equation, third value. Similarly, if I want to write k24, that will be f2 function. This will be the same. This will be the same. Okay. So this is what it is. Okay. So this from here we will find the k values. Once we have found out the k values, we can find out the u values. How we can find out the u values? The u I plus 1, u1 of I plus 1 will be equal to u1 of I plus h by 6 k11 plus k12 plus k13 plus k14. This will be 2 times and this will be 2 times. Similarly, if I want to find u2 of I plus 1, that will be equal to u2 at ith plus h by 2, h by 6 k21 plus 2 times k22 plus 2 times k23 plus k24. 24. Okay, this is what the formula is. Now we'll write its computer program. Okay, so to write its computer program, first what we need to do? First we need to discretize. We'll discretize the domain. Okay, first we will discretize the domain. Then we will define the function f1 function. Okay, then we will define the f1 and f2. Okay, once the domain is discretized, we will define the f1 and f2. Then we will find the k1 1 k12 k13 k14. Similarly, k21 k22 k23 k24 values at each grid point. Okay, for each grid point we will find that. Then at each grid point in the same we will find out the u1i and u2i. Okay, once we will find the u1i, our problem will be solved, since this u1i will be equal to u1 will be equal to y, so u1i will be equal to y1i. That's so the problem will be solved. Okay, so first we will discretize the domain. Okay, so now I will stop share from here. So what I am opening here. Okay, so I will share the screen now here from my computer. Okay, so just give me 2 minutes. I will share the screen from here. So now let me open the notes. Okay, so share screen. Where is the option for share screen in my computer? Okay, from here I can share the screen. Are you able to see my screen now? Okay. Okay, so you are able to see my screen. Huh? So first we will discretize the domain. Then we will define the function. Okay. So first I'm just writing clear all PLC. So my initial value is what? x0 is what? X0 is 0 and XL is what? 10. Here XL is 10. Na? From 0 to 10, I need to do that. Now I need to take the step size h equal to what? 0.01. Okay, this is my h. Now I am considering h equal to 0.1. Once we will make the program, I will just change h to 0.01. Okay. Now, then what will be the number of number of steps? What will be the number of steps? N will be equal to, in bracket, xl minus x naught divided by h. Okay. So I just want to just calculate it whether everything is going well or not. So yeah, so 100 आ गया. Everything is good. Now I will define my x. X will be equal to zeros of what will be the number of element? Number of element will be n plus 1. If n steps, so number of grid size will be n plus 1. So this is what this is my x. So now grid generation. Okay, so grid generation. Now I'm doing the grid generation for I equal to 1 to n plus 1. Okay, so here in MATLAB, indexing start from 1. That's why I'm really writing I equal to from 1 to n plus 1. Okay, so x of I will be equal to what? X of I will be equal to x of I minus 1 plus h. Okay, now there is one trick. I will start from I equal to 2 and I know x at first will be x1 will be what? X1 will be what? X1 will be x naught. Okay, so now if I do this, I run this. So it has run now. If I check the x is what? The 101 element. So I have discretized the domain now. Okay, so now I need to define the u now. So u1 will be what? U1 will be similarly control C. I am initializing u1 to 0. Similarly, u2 to 0. Okay. And what is the initial value we have? Initial values. Initial value is what? U1 is what? U1 is what? U1 is what? U11 is 0 and U2 of 1 is what? U2 of 1 is what? 1. This is the initial conditions. Now the defining the function f1 and f2. Now I am defining the function f1 and f2. Okay. So f1 will be what? F1 is a function of x comma u1 comma u2. So this is what this is my f1. Na? This is my F1. So F1 is what here? U2. F1 is U2. And similarly, I need to define what? I need to define F2. So F2 is what? F2 is minus U2 minus U2 minus U1 plus sine of X. Okay, sine of X. This is my F2. So let me run that, whether everything is clear on everything is working well or not. So yeah, so this F1 and F2 has been created. Now what we'll do, we'll apply the fourth order Runge-Kutta method. Fourth order RK method to solve second order initial value problem. Okay, so if I want to find K11, okay, so K11 will be what? Let me check in my notes. K11 is what? K11 will be what? F1 at xi yi. F1 at xi yi means what? F1 at xi, U1 at I, and U2 at I. Okay, so K11 will be what? K11 will be function of F1. And F1 will be at what point? X at I, okay, comma U1 at I, comma U2 at I. Okay, so this is my K1, or from where my I will go? I will go from, I will be equal to 1 to I will go from 2 to, since at 1, at first point and last point we know at first point we already know the value. So I will go from, suppose 1 to n plus 1, okay, then in. Okay, so this is my K11. Now if I want to find K12, sorry, K12, K21, second equation, first value. So this first one is equation number, second one is what? K number. So K2, this will be equal to same value, only the function will be F2. Okay, similarly, if I write now K1, 2 and K22. So K12 will be what? Xi plus h by 2, right? Here will be U1 I plus, in bracket, h multiplied by K from first equation, first value, divided by 2. Control C, Control V, plus here will be K from second equation, first value. Okay, now everything else will be same in the below. only F1 will be replaced from F2. Okay, so this is my K22. Now if I wish to find out the Control C K13 and K23. Okay, so I want to find now K13 and K23. Okay, so this will be the same. Here will be what? From first equation, second value, from second equation, second value. Here also from second equation. Okay, now K14, K24. Okay, so this will be what? Directly H. Now U1, this will directly H. First equation, third value, second equation, third value. Okay, then I will directly copy this. Okay, so I have defined the case. Now what I will do, I will find out the U. So U1 of I plus 1, I plus 1, this will be equal to, U at I plus H by 6. Okay, H by 6, K11 plus 2 multiplied by K12 plus 2 multiplied by K13 plus K14. Okay, so this will be my U1. Similarly, U2 will be what? I directly paste that. So similarly, U2 will be what? Here also U2. Now K21, K22, K23, K24. Okay. Now I have defined. Now if you see at how many elements we have? N plus 1, no? N plus 1 we have. Here also we have N plus 1 element in the grid. So when I equal to N plus 1, it will try to define I plus 2 term. That's why I need to go from I equal to 1 to N only. Okay. Now suppose if I just select it and evaluate. So it is showing some error. What is the error? Indexing problem. There is some parentheses and indexing errors are here. So K11. Okay, there will be a multiplication sign here, na? Here also and here also. Now if I control A, see, we have found out the U1 and U2. There are some values of U1 and there are some values of U2. Now suppose I want to plot it, whatever we have got. So I am writing plot X comma U1. Okay. And in the same plot, I want to plot X comma U2. Okay. But I want to plot in same plot, so I need to write the command hold on. Okay. To open the new figure, I need to write figure. Okay. So if I now run it, control A. See. So which one is U1 and which one is U2? I don't know. So I need to write that. So first one is U1 means first one is Y mere. So I need to like ligand. First one is what my? First one is Y and second one is what? Second one is my U2. U2 is what? Derivative. So dy by dx. Now simply if I cut the figures, I again plot it. See, so the blue one is my Y. So at 0, Y is 0. See, and this orange one is my dy by dx. At x equal to 0, Y prime is what? 1. This is the initial condition. So this is the plot we will get. I hope you have understood whatever we have written. So similarly here also I have written, and I have done some appearance thing so that the figure looks good. Suppose I just want to run this. So if I run this, so this is what we will get. No. So this is my Y and this is my derivative. Okay. Just we have defined the F1 first we have defined. If you suppose if you want to solve some different initial value problem for different ODE, you need to just find out this F1 and F2. You need to replace here. And again, the boundary condition, whatever you get, sorry, initial condition, whatever you get, you put here. And discretization, you change here according the gate size. And you solve. Okay. Suppose I want to go for 0.01 step size, 0.01 step size. Now step size I have improved. I run again. See, more or less the same plot it will come. If I reduce the grid size to 1, what I will get? See, now it is kind of non-accurate. So 0.01. Clear? Please respond. So have you understood whatever I tried to teach? So let me again share my screen from my iPad. So are you able to see my screen? Okay. Yeah, now you are able to see now. So what we did today. So in week 7, we were studied about the ordinary differential equation. So first we have seen what is the ordinary differential equation. Then we have seen the methods, analytical method, how we can solve the ordinary differential equation. That are kind of revision. Separation of variable method, exact ordinary differential equation, homogeneous ordinary differential equation, how to solve linear ordinary differential equation using integrating factor, Then the Bernoulli equations. This is also kind of that equation. This Bernoulli equation can also be converted into a linear ODEs by some substitution y z equal to 1 upon y, whatever the term will come here. Suppose here y equal to n. So what we will do, we will assume z will equal to y to the power n minus 1. Sorry, minus 1 minus n. Okay, so this will be my z. Then we have seen the numerical methods to solve the ordinary differential equation. So two kind of problem can be arises. First is initial value problem. Second is boundary value problem. Initial value problem can be solved using Euler method or Rungge-Kutta method. Euler method can be considered as the first order Rungge-Kutta method. So we have seen then how to use the Euler method and various order of Rungge-Kutta method to solve the initial value problem. Okay. Then higher order eigenvalue problem. Oh, sorry, not initial value problem. This can be solved by converting the nth order ordinary differential equation into a n first order ordinary differential equation. We have also solved one second order ordinary differential equation and also written its computer program. Okay. Then the initial value problem example we have seen in population growth method. Then we came to a boundary value problem. The boundary value problem can be solved either by converting it into a initial value problem. That method is known as a sorting method, or it can directly solve by changing it into a system of linear equation. And how we can change it into a system of linear equation? By using either finite value method, finite element method, or finite difference method. Here we will see only finite difference method. Okay. So then sorting method has been discussed. For that, we have one boundary condition. So we assume two initial conditions such that whatever the solution came, that should relate to boundary condition like that. Suppose if I have f prime equal to 1, so if alpha came and beta came, so alpha and beta should come, one should be less than 1 and other should be greater than 1. So A, B assumption should be like that. If condition is satisfied, then we can assume new guess using the bisection type of algorithm A plus B by 2, f double prime at 0, A plus B by 2. Then from here we find the boundary condition. Suppose that come to gamma, then one of alpha or beta will be replaced by bisection method. Okay. Then we have seen the finite difference method. There we have seen a practical problem, which is a one-dimensional heat conduction in fins or heat conduction in extended surface. There the ordinary differential equation first non-dimensionalized. Then how we can solve this? First by discussing the domain. Then we discretize the governing differential equation. Then we discretize the boundary condition. After all these three steps, we have found a system of linear equation Ax equal to B type. This can be solved by any linear solver, but this came as a special type of matrix or special type of system that is known as tridiagonal system. Tridiagonal system. Okay, this is tridiagonal system, and this tridiagonal system can be solved using the Thomas algorithm, and we have discussed about the Thomas algorithm. Now, in coming week, we will use this Thomas algorithm to solve ordinary differential equations. Okay, clear? So now I will stop sharing. Okay. Now I will leave from here. Now I will off the recording.